Hi, this is our second part of the GI tract and the secretions. This time we talk about the secretory activity of the GI tract. So we'll start with the stomach and then we head down to the duodenum. There are some secretions happening at the duodenum level, and also from the liver and the pancreas. Both of them will empty the their secretions into the duodenum. Then we'll head south to the jejunum, and after that there isn't much secretion added to your chyme. So let's start with the stomach, and as you see here, the different things added to the chyme will be enzymes. Generally you're releasing those enzymes as proenzymes or zymogens. These are things that will become enzymes later on after activated. Example for that is the pepsinogen and trypsinogen. These are proenzymes or zymogens. They require activation, and this is a good process because you don't want these protein chewing enzymes to destroy the cell's own proteins. In addition to that, we're going to have some mucus secreted, and that's very important both as for lubrication function but also to provide protection. For example, in the stomach, you want the stomach to be protected from the digestive enzymes and the hydrochloric acid by that kind of mucus. We have some ions being secreted. Example for that, the hydrogen ions, for example, are secreted in the stomach, and that gives the HCl. Also the chloride is secreted in the stomach. When we head south, the bicarbonate would be secreted in the small intestine to neutralize, of course, the acidity of the stomach. We have some water, and we're going to talk a little bit about the processes through which the intestine, for example, is capable of neutralizing the acidity of the stomach. How is the acidity of the stomach formed? The proton pumps that are present in the stomach. We're going to talk about that in this presentation. So if we start with the gastric secretion, and this is a very, very, very important slide. The different types of cells, we need to remember the two of them, the surface and the neck cells, will be secreting the mucus for us. So we have superficial epithelial cells and mucus cells, and then we have stem cells that will regenerate damaged cells, because of course the stomach is undergoing a lot of trauma from the acids, from the enzymes, and the cells will have a short life, and those cells have to be replaced regularly, and that of course would be the function of the stem cells sitting here. After that, we're going to have the parietal cells, and the parietal cells have two very, very important functions: HCl secretion and intrinsic factor. And you need to remember that parietal cells will have HCl secretion and intrinsic factor. Then we go to the chief cells, and the chief cells are going to secrete to us proenzyme called pepsinogen. Proenzyme called pepsinogen. The activation of pepsinogen later on will result in making pepsin, and we will see that in the next few slides. And then we have the final cells is the endocrine cells, and that will be or the G cells, and that will be secreting to us the gastrin. Gastrin has a very important function in the digestion, and we're going to see the function in a very short bit. So once again, we have the parietal cells secreting HCl and intrinsic factor, the chief cells giving you pepsinogen, and the endocrine cells giving you gastrin. Okay, So let's look at greater details into that. We have the mucous cells, we have the neck and the surface cells. They will give you protective mucus. These are very, very, very important. It will give some bicarbonate as well, but to the underlayer here, to the submucosa, and it's important because you would like some kind of protection. Anyhow, the parietal cells, these are important, very important cells, will give you HCl, and it will give you also the intrinsic factor. Then we have the chief cells. The chief cells will give you the pepsinogen, and the pyloric gland G cells, and these are also called the endocrine cells. They will secrete to you gastrin. Okay, so in the mucosa we're gonna have in the mucosa layer we're gonna have mucinous cells, parietal cells, chief cells, and we have the antral mucosa, and then all the way at the antrum we will have mucous cells, endocrine cells, G cells, and D cells will give you somatostatin. Somatostatin has an important function in regulating your appetite. It also talks back to the pancreas to start the release of insulin. It talks to the intestine to slow down the absorption, and so it has a lot of endocrine cells, the D cells. The G cells, we already know, it gives you gastrin. So the gastric juice, here we go. We're going to start with the pepsin, and the pepsin is secreted as pepsinogen. Pepsinogen will be activated into pepsin later on. In the presence of acidic pH, you accelerate the conversion into pepsin from pepsinogen. And once you have pepsin, pepsin can also activate itself by cleaving pepsinogen. So once again, pepsin gets activated in the presence of acid, but once you have the pepsin being the active molecule, it can also activate itself by activating the pepsinogen, where you are cleaving a small peptide to release the pepsin later on. Pepsinogen, as we agreed before, is secreted from the chief cells. You need to remember that. And the parietal cells, if you remember, it gave you the HCl and the intrinsic factor. The pepsin activity is best when it's acidic, which is no surprise here because of course we have a very acidic nature in the stomach. It will be inactivated in the duodenum, and you will see that's because of the bicarbonate secretion both from the pancreas and from the duodenum. Immediately the acidity will be neutralized, and therefore the pepsin activity is not going to be of significance at this point. Alright, so another thing that is secreted, but this time is from the parietal cells, is the intrinsic factor. It's a glycoprotein, and it's very important for the absorption of vitamin B12. It will bind vitamin B12 and facilitate its absorption. The lack of the intrinsic factor, for example, if someone has infection in the stomach, someone who removed part of the stomach, we call that gastrectomy, these people will not have enough intrinsic factor, and therefore they can suffer from anemia called pernicious anemia, where they are unable to make more red blood cells. Okay? Alright. The other thing the parietal cells are secreting is HCl, and the way they secrete it is by sending hydrogen ions using hydrogen-potassium exchange. And you can see the picture here. We have an antiport that will take the hydrogen ions out and will bring in from the lumen, from the inside the stomach, the potassium instead. At the same time, you have a chloride being pumped out, and also by diffusion, not by really active mechanism, but just by diffusion from the high level here to the low level on the other side. And that will combine the chloride on one hand and the H on the other hand, so you have your HCl. In order to bring some more, you have to combine the carbon dioxide with H2O, and that will give you HCO3. HCO3 will be exchanged with chloride. Remember, you always want a steady flow of the chloride and the hydrogen ion. This is how they come. So you are combining carbon dioxide with water. that will give you H2CO3. Actually, it gives you straight HCO3 and hydrogen. HCO3 will be pumped out in exchange of chloride, and H will be the one here exchanged, and therefore here's where you got your H right here, and here's where you got your chloride right here. This guy here is an active pump, where you're pumping the hydrogen out and bringing in potassium. People who have high acidity or reflux disease, they use special pills that will disable this, and we call that proton pump inhibitors. Okay? Alright, so this is where the HCl comes from. Your parietal cells release approximately 1 to 3 liters of HCl per day, and that will reduce the pH to around 1 or 2 inside the stomach. Sounds good? So, what stimulates the HCl secretion from the parietal cells? We have the histamine. Histamine will be secreted from enterochromaffin-like cells inside the stomach, and that will stimulate the histamine secretion. Acetylcholine, that's parasympathetic stimulation, will stimulate also the parietal cells directly. The third stimulant is the gastrin, and that's produced by the G cells in the antrum, the stomach, and in the duodenum. And that can be stimulated by amino acids. That means you ate a lot of proteins, and so you will need some more acid to deal with that. Stomach distension, if the stomach is full, then gastrin is released. If you have gastrin being released, that will stimulate the parietal cells to secrete more HCl. And then there is a third thing here, which will be the gastrin releasing peptide, and that will be through vagal nerve stimulation, will release the gastrin from the G cells directly. Once again, if you have the gastrin being secreted, it will go back to the parietal cells and will activate the parietal cells to give you HCl. Okay, so these are the stimulants for the gastrin secretion. Once again, histamine, that comes from enterochromaffin-like cells, acetylcholine, gastrin. Acetylcholine is the parasympathetic stimulation, the innervation of the stomach by the parasympathetic system. The gastrin, that is coming from the G cells, from the neuroendocrine cells that are present in the stomach. Whatever the reason is, if we have gastrin being released or activated, now gastrin will start to stimulate the parietal cells into making more HCl. Okay. In addition to that, we have gastric mucus, and we already agreed that the mucus has several functions. One of them is lubrication, but the second one is really protection, because you would want to protect your mucosa cells in the stomach against the very, very acidic nature of the secretion. We have two different kinds of mucus. One of them is from the surface epithelium, and the other one is secreted from the neck epithelial cells. The neck epithelial cells is more acidic nature, the mucus, and whereas the epithelial cells gives you a salty kind of aqueous fluid. Both of them are very important in protecting the wall of the stomach against the acid nature and the other secretions. Okay? We go down now, we're done with the stomach, and we will go down to the intestine. The first thing we will face is the duodenum, and we see here the duodenum. One of the most important things that will be secreted at the duodenum is bicarbonate, HCO3, and the reason is we would like to neutralize the acidity of the stomach. Or the stomach secretion. So as the fluid is passing from the stomach to the intestine, you would want that to be neutralized by HCO3 or bicarbonate, and that will be done by Brunner's glands, and these will secrete to you HCO3, and you can see a picture of the Brunner's glands here. Okay, so other than that, we talked already about the bicarbonate being secreted from the duodenum, but they're also secreted from the pancreas. The pancreas gives you a lot of bicarbonate, and we will see the bicarbonate in a little bit, how they are created inside the pancreas. Other than that, we will have enzymes, and mainly they are pancreatic enzymes. Again, they are zymogens. They're not active state enzymes, but they will require some kind of activation in order to become functional. We'll talk about that, like trypsin. Initially it is trypsinogen, chymotrypsin, it's chymotrypsinogen, and so on. All of these enzymes have to be activated first, and we will talk about that in a short bit. These are digestive enzymes that will be secreted into your intestinal lumen. The bile will have the bile salts, among other things, like the bilirubin. After it's cleared from the blood, it is going to be also secreted or excreted into the intestine. We have a lot of conjugated chemicals, toxins that will be also secreted along with that, and we will talk about that in a little bit. Then we have the mucus being secreted also from the intestine, and the intestine also have some endocrine agents. We'll talk about secretin, and we will talk about gastrin in a short bit, and cholecystokinin. Gastrin, we sort of talked about it already, the function of which is to stimulate the parietal cells to secrete HCl. That's the function of gastrin. But we have other hormones such as secretin, and we also have cholecystokinin, and we will talk about them in a very short time. So the pancreatic enzymes are secreted in response to the presence of chyme in the intestine. The intestinal enzymes are activated in stepwise. So first we have an enzyme called enteropeptidase, and that's coming from the intestine, and that will convert trypsinogen into trypsin. Once you have trypsin, then trypsin will be able to activate other kinds of enzymes. So enteropeptidase is an enzyme that is capable of activating trypsinogen into trypsin. Trypsin itself, when you have it, will be able to activate other enzymes, and you will see that in the next slide here. So here are the pancreatic secretions. You have trypsinogen and lots of other enzymes here that are, all of them are inactive. How do I know they are inactive? Because they have gen in the end or pro in the beginning. So we have procolipase, we have prophospholipase, we have procarboxypeptidase, and the chymotrypsinogen, because it has a gen in the end. All of these guys are inactive. Also trypsinogen is inactive, but that guy gets activated by an intestinal enzyme called enteropeptidase that will cleave the trypsinogen into trypsin, and the trypsin itself will be able to convert these guys into the active enzymes that will be able to digest peptides, lipids, and phospholipids as well. Okay? All right. We talked about this before, into how does the pancreatic cell make HCO3. If you remember, it's the opposite of how does a stomach or parietal cell makes hydrogen ions. More or less the opposite. So let's talk about that. We're going to pick up carbon dioxide, combine it with water. In the presence of an enzyme called carbonic anhydrase, you will create HCO3 and hydrogen ions. We don't want the hydrogen ions, so we're going to exchange that with sodium. Let's stay with the HCO3 for a second. HCO3 will be shifted out to the lumen, and we're going to take instead of it chloride. So we are pushing HCO3, and we're going to take chloride instead. Then the chloride itself will be switched again outside by cystic fibrosis transmembrane conductance channel, CFTR, and that will pump the chloride into the lumen as well. Okay, so this is how we got a lot of HCO3 into the pancreatic secretion, again by combining carbon dioxide with water with the carbonic anhydrase. You created HCO3. HCO3 will be exchanged with the chloride, and you want to keep recycling the chloride, so whatever chloride you bring from outside, you send it back in, because you shouldn't accumulate too much chloride inside the cell. Sounds good on that end. But on this end, we have the hydrogen ion. The hydrogen ion will be exchanged with sodium, so you kick out the hydrogen. It's a proton exchanger, and you're going to bring in sodium instead, and sodium will be exchanged with potassium later on, because we don't want sodium inside the cells. We would like potassium instead, and that would be exchanged here by a sodium potassium pump exchanger. At the same time, you have MKCC transport protein, which is short for sodium 2 chloride and 1 potassium, NKCC, and that will bring in sodium, 2 chlorides, and potassium. If you notice, sodium has 1 charge, potassium has 1 charge, and chloride has 1 minus charge, negative charge, but you're bringing in 2 of them, so the net result here, of course, is neutral. Sounds good? So this is how the pancreatic cell will create, or the intestinal cell, like the one we saw in the duodenum, makes HCO3 for you. Sounds good? So let's move on to the intestinal hormone. So we did talk about the enzymes like enteropeptidase, but we also have intestinal hormones being secreted other than gastrin, which we did talk about before. We have a hormone called secretin, and that will be released from the duodenal S cells. S cells will give you secretin, and only when the pH drops to 4.5. That means when the stomach is emptying. The secretin will say, wait a second, everyone needs to halt. We have too acidic medium here in the duodenum. You need to slow down the emptying. So the secretin would go back to the stomach and say, slow down a little bit, we're not ready for you. Okay, that's a hormone. Another hormone, cholecystokinin, although it is associated with the control of the appetite, it also will talk to your gallbladder and will cause the gallbladder to contract. Therefore, you have the bile being secreted or pushed into your intestine. In addition to that, it also stimulates the release of the pancreatic enzymes and the bicarbonate. So we're going to remember now that the secretin is from the S cells, and the cholecystokinin, CCK for short, is coming from the I cells. Both of them are coming from the duodenum. Sounds good? So you need to remember those two, because I guarantee there will be more than a question coming in the test from the secretin and the cholecystokinin. Okay, so we're done with the secretion from the tubes themselves, from the gastrointestinal tract. Then we go to the accessory glands. Here we talk about the liver. First, let's talk about the structure of the liver. It is about 3 pounds, and it's soft. It has lots of functions. It has detoxification function. It deals with glycogen breaking, storage, protein synthesis, protein metabolism, protein anabolism, catabolism, meaning making and breaking of protein. It makes a lot of vitamins. It makes a lot of coagulation factors, but from the digestive perspective, it secretes the bile, and we will talk where the bile is coming from, and that is very needed for the breaking up of the dietary fat, or what we call emulsification. That's making the big droplet of fat smaller. And the liver, everything has to go through the liver from the portal vein here, and or the portal hepatic vein, and it will be detoxified here inside the liver before it goes into the hepatic vein. So things that you take, pills, drugs, things that you absorb from the intestine will have the first exposure here. That's what we mean by first pass effect. Okay. The surface anatomy of it will vary, but anywhere between rib number 7, rib number 11 on the right, and of course it will taper towards the left. We have 4 lobes, and we need to remember the names of the lobes. We have right and left, and we have the caudate, and that's the one from the back that's towards the head, and then towards the tail, because cauda means tail, and then we have the quadrate, that's the one that is square. So we have left, right, the tail lobe, which is towards the bottom, and then we have the quadrate lobe, which is a rectangular or rectangular in shape. That's why we call it quadrate lobe. Okay, so again, the liver is getting blood from the arterial supply, that's called the hepatic artery, and it's getting all the venous drainage from the intestine and from the GI tract in what we call hepatic portal vein. Sometimes it's referred to as just the portal vein. The two blood will mix together in the liver, and then the blood will drain from the liver as branches from the hepatic vein that will end up all the way into the inferior vena cava. You see here the hepatic vein or the hepatic portal vein, and then you see here the hepatic artery, and you see here the bile ductule, and we'll talk a little bit about that later on. But anyways, the blood is coming from here, from both arterial and venous end. This is the hepatic portal vein, this is the hepatic artery. They will mix together and they will form what we call sinusoids. These capillaries don't have continuous epithelium at all. Actually, they're lacking the epithelium, or what we call the endothelium, and therefore the hepatocytes, which are the liver cells, will have direct access to the blood that's inside them, and that will allow the liver cells to manipulate the content by detoxifying chemicals, by secreting proteins directly into the blood. When everything is all done, then it will collect the blood into central veins, and when you collect the central veins together, that will lead in the end into the hepatic vein, and the hepatic vein will empty into the inferior vena cava. Okay, so here it is again. Here you have a branch of the portal vein, or what your book sometimes refer to as hepatic portal vein, and here is the branch from the hepatic artery. The blood will mix together and will end up with the central vein. The central vein will collect together into what we call the hepatic vein, and the hepatic vein will empty into the inferior vena cava. Alright, so at the same time, these cells will also secrete the bile. They pick the bilirubin from the blood, they secrete other stuff here into your bile canaliculi. This is the bile canaliculus here, and that will collect into the bile ductule, and when you combine the bile ductules together, then you will end with the common hepatic duct. And the common hepatic duct, you will see it will be combined with the cystic duct into what we call the common bile duct. Okay, all right, so the bile is a digestive fluid that has bile salts. That is the main active ingredient here, aside from water. These are steroid bile acids. These are conjugated steroids, so you take the steroids and add bilirubin into them, or not bilirubin, I'm sorry, GST into them, which is glutathione or glucurinated steroids. So all of that will be secreted into the bile, and collectively we call that the bile salt. The remaining, we have pigment. That what gives the stool the color. It's bilirubin, and that's coming from the breaking apart of the red blood cells in the blood. You take the hemoglobin, and through a process you will conjugate that hemoglobin into making bilirubin, and that bilirubin will be secreted with the bile secretion. Other things that are present in the bile: a little bit of cholesterol, a little bit of mucus. The main thing we need to remember is the bile salts, and the bile salts are very, very, very important in breaking the fat into smaller molecules in a process we called emulsification of lipids. Okay, so the contraction of the gallbladder, which is keeping and concentrating the bile for you, is stimulated by the cholecystokinin. If you remember from the eye cells in the duodenum, will secrete the cholecystokinin, and then that will result in the squeezing, the contraction of the gallbladder wall, and the release of the bile salts into the intestine. All right, so here is the gallbladder itself. Here is the hepatic duct, the common hepatic duct, and that will unite with the cystic duct here and into the common bile duct that you can see over here. Later on, the common bile duct is going to form with the pancreatic duct, a hepatopancreatic duct, and then that will open into the hepatopancreatic ampulla. Okay, so but anyways, let's stay with this, with the gallbladder. The gallbladder will have the fundus, will have the body, and will have the neck, and will have then the cystic duct itself that will unite with the bile duct. These are, and of course we have smooth muscle fibers here. Remember that the gallbladder is supposed to squirt bile salts and bile secretion to the intestine when it's stimulated by cholecystokinin, and that of course will mean that they have musculature along the walls of the gallbladder. Okay, all right, so here's a picture again of the gallbladder, although I doubt that this can be asked in a test, but you can see here that this is the common hepatic duct. You can see that here, and this is the cystic duct, and here you see the gallbladder uniting into what we call the common bile duct, and the common bile duct is gonna unite with the pancreatic duct, as you can see here. This is the pancreatic duct. Okay, all right. Sometimes occlusion happen in the gallbladder, and that results in stones being built up and in what we call gallstones. And sometimes there is wrong metabolism that happens in the gallbladder that also will result in excessive content of the cholesterol, and then you will start to form these secretions. Sometimes it's cholesterol is the problem, and sometimes calcium is the problem. Okay, in some people, for example with drinking, with hepatitis, with other viral infection, people can start suffering from liver cirrhosis, and the liver, instead of being smooth, it will be bumpy and lumpy, and that can lead after some time into hepatocellular carcinoma. The reason is the normal liver will start to have some kind of damage. This damage can be fatty degeneration, or what we call steatosis, and that will be from alcohol mainly, but there are other infections that can also cause steatosis. And here is the cirrhosis, and you can see here foci of growing newly growing hepatocytes or liver cells will start growing and make these bumps and lumps into the wall, and that's easily palpated. When you touch the liver, you will see that the surface of the liver being bumpy and has tiny little lumps on it. Also with MRI and ultrasound will show this kind of surface.